Okay, so now that we know how to set up a plane model in this program, it kind of begs the question, what was the point of that? So in this video we're going to have a look at some of the analysis features, just a few of them, actually only two, because they're the only ones that I really use. Again, I can only tell you what I really know and I've tried. Other than that, I have no idea about a lot of this stuff. Just a couple of things that I wanted to mention first though. You may have noticed here that the colors of these highlighted sections are different. So I've made the current airfoil section purple, and the lines are a bit thicker too, and the selected wing section is in green because I did quite a bit of complaining in the last video that these were hard to see because they were all red. So I thought, why don't I try and do something about it myself? So I've forked this project on GitHub, and you can get these changes from my fork if you like, although I have also changed some of the CMake files to help it build on my Fedora Linux. So if you do get my changes, you might want to just look at the places that I've changed other than the make files. There's only a handful of lines because we're just it's just to change the colors. So you might want to look at those changes and apply them yourself rather than getting my entire fork. Anyway, another thing I wanted to look at was where is it? In this wing section tab, somebody pointed out in the comments of the previous video that there's a section here with these radio buttons which I completely ignored in my previous video because I was kind of baffled actually by what this was when I first saw it, and thereafter I just ignored it. But what this lets you do is, you'll notice that the ones that have a check in them or a dot in them, these are the ones that are actively editable over here in our inputs. But you can change that to something else if you want to. But there's a reason why you can only select certain ones of them. A little bit simpler way to explain this might be, let's say you have a rectangle and you want to, there's three characteristics of a rectangle: the height, the width, and as a function of the height and the width you have the area. So you can say, I want a rectangle that's 5 units wide by 2 units high, then the area would be 10, right? But you can't specify all three. You can't say, I want the rectangle to be 5 units high, 2 units wide, and area of 25. It just doesn't make sense. So that's why some of these are disabled, because they're kind of linked in that same kind of way. They depend on each other. And the reason that there's two, I think this is the way it works. The reason that there's two enabled in this row at the bottom, for example, is because in these three columns, these columns are linked to each other in a certain way. So at the moment we have span, root chord, and tip chord, and I'm defining this section here. And the last one at the bottom, this is the one that I actually wanted to use. So thank you very much to the person who commented about this. What I wanted to do was set the sweep of the trailing edge, which is this secondary sweep one. And I wanted to set that to 0 so that my trailing edge of this particular plane would be 0. But you can see what I've done is I've got this to approximately a sweep of 0 by editing the chord and the tip length, the root chord and the tip chord, and that's took a long time. Every time I wanted to change something a little bit at the leading edge, I had to come back here and set the chord length so that I would get approximately straight trailing edge. But what I could have done is just check one of these radio buttons, and that would, for example, if I check the middle one, that would replace the root chord. If I check the second one here, that would replace the tip chord. So if I click here, you'll notice that now tip chord is disabled, but I can change the trailing edge sweep from 0.22 degrees to 0, and that will give me a nice flat trailing edge. So that would have saved me a hell of a lot of time. Anyway, just thought I'd mention that before we moved on. So the only two analysis features that I'm going to look at in this video are the projected area and the VSP area arrow. I'll also look at planar slice, but I'll do that in a future video where I describe the process of taking the output of this and moving it into Blender and QCAD and actually trying to make something with it from foam slices. So projected area, let's just put this in that kind of a view first. So projected area lets you measure that, well, the main thing it's useful for is measuring the wing area. So projected area, and we have a target set, and this is what I was mentioning before about you can set it to measure for all of the objects in the scene or just for the shown or the not shown ones, and looks like there's a way to create labeled sets too, but I haven't figured that out. But anyway, when I'm measuring the wing area, and I'm doing this for the purposes of determining wing loading, I might want to exclude the tail because that's not really a lifting surface. It's sort of, you know, trying to hold the tail down. So if I go over here and put no show on the tail, and then I select in here the shown only. And the axis that I want to project on is the Z axis, so I would click here, and I think then I just do start, and that will give me this mesh geom object in here, and it also tells me the area is 40. Now this 40 will be meaningless unless you've set your plane up to be of specific dimensions. So if you're using centimeters for all your units in the plane, this will be square centimeters. Actually, it might be, well, it will make sense if you're actually using sensible units for your model. And you can sort of look at it there just to, I guess, visually check that you got the exact thing that you're looking for. So let's move that up. So there we go. Alright, so that's just one way you can measure the area if you want to. And typically you don't want that anymore, so then you would just delete it to get rid of it. Now the other analysis tool that we're going to spend most of our time looking at in this video is of course VSP Aero, but before we do that I just want to go over a few concepts to make sure that everything is clear when we come to looking at that tool. So bear with me here, it's a little bit basic for some of you I would imagine, but suppose we have some airflow coming in from the left towards the right, and we have a piece of foam board or something. Well, it's brown, but oh, I guess it's the waterproof foam board that the flight test guys use. That's why it's brown. Yeah. Anyway, so as a result of this airflow and the angle, we would get a drag. We would also get some sort of a component of lift as well. Yeah, I know. You've seen this 1,000 times. Just bear with me. Now, the magnitude of these in the real world, we would measure this in pounds or kilograms or newtons or something like that. But it's not the exact number of newtons or kilograms that we really want to consider, because that will depend on how fast the wind is flowing and how large this wing is. What we really want to check is the ratio of lift to drag, because that will determine at any wind speed and any size how efficient this thing is. So in some of the graphs that we're going to be looking at later, we'll look at something called the coefficient of lift and the coefficient of drag, which are dimensionless in that they're not measured in pounds or kilograms or anything. The only thing that's really important is the ratio between them. And we also have to consider that we have other forces here. So there's, well, weight, gravity, and then we have thrust going forward. But the thing about these two forces down here is they're a lot easier to adjust in the real world. For example, the weight we can adjust by using packing tape instead of fiberglass or something, and the thrust we can adjust by different type of motor, or 4S battery instead of a 3S battery or something like that. But these two here, they're a little bit harder to figure out, so that's why we're using a software package to help us with that. Another concept that I wanted to look at was, as well as forces that push this thing from side to side, we also really need to consider, and this is where this software really helps, what kind of a twisting force or a moment will be applied to this piece of foam board. And again, we have the air coming in from the left to the right, and this purple thing will be the center of mass of this foam board. So let's say we've stuck a lead weight on here or something, and I think we can all see what's going to happen in the first two of these cases. The center of mass is, well, if the angle of attack versus the wind is like this, it's going to be turned around because there's a larger aerodynamic area on the back, and it's going to eventually end up facing into the wind like this. So if the angle of attack is high, it's going to incur, or it's going to see a anti-clockwise moment, or a torque, or some sort of a twisting force is going to be the result of that. If the angle of attack is negative, it's going to see a clockwise twisting force, so it's going to end up like that. And this is pretty simple for these two cases, it's obvious. But the point is that the angle of attack relative to the wind is going to determine which way this twisting force goes. And this also has a name which we're going to be looking at in the program, and this is going by the name of coefficient of moment, I think it is. And again, it's a coefficient, so it's not a real world measurement like foot-pounds of torque or anything like that. But it's just a magnitude, and it's called coefficient, well, CMY is what it's called in the graphs. So just remember that this is a force or a torque turning it one way or the other. And when it gets to this point, because it's now perfectly in line with the wind, we wouldn't really have any coefficient of, well, it'll be 0, right? So let's just say that the CMY equals 0 at that point, like that situation like that. And for a perfectly flat sheet, flat plate like that, it's just going to be facing straight into the wind. However, we're not flying perfectly flat sheets. So let's say we had a little bit of something sticking up at the back, like a tail or something. This is going to get in the airflow, and instead of ending up perfectly flat, I think we could again see it's going to end up at this point. So the coefficient of my being 0 is at some angle. In this case, it looks like angle of attack of maybe 2 degrees or something like that. Now the question that we really want the software to help us with is, when we have a very complicated set of things moving through the air, what is the angle of attack that we're going to end up with when the moments are 0? So there's two things to consider. What is the natural angle of attack for this bunch of surfaces, and what is the lift to drag ratio at that angle of attack? So that's what we need to figure out, and we're going to use just two graphs really to figure that out. At least this is how I do it. Again, I don't really know if this is how you're supposed to do it, and there are a whole lot of other numbers and bits and pieces in these graphs that you can look at, but this is basically all I've been doing when I've been making my planes. So hopefully that all makes sense, and we'll start by looking at what happens with this simple default wing, just to get a hang of things. So I'll start this here, and there's a huge bunch of settings. I'm only going to look at a few on this first overview tab, and maybe 2 I think on that advanced tab. Where shall we start? Let's just run it and see what happens, eh? So when we click Launch Solver, you can see some work going on in the background there. Unfortunately, it doesn't let you know how long it's going to take, because some of these things can be quite long, but you'll just have to get the hang of looking at how quickly it's progressing to figure out how long it's going to take. Anyway, we have a graph shown on this Results Manager window. There are 3 sets of data here, and we can select individually to show whichever one we want there, or all of them like this. And what we're looking at here is the load distribution. So this the center of the graph here at 0 is span location Y, so this is right in the middle of the plane, and then at the wingtips we have less load being taken up. Now the reason there's 3 of those is because under the flow condition setting we have number of points set to 3, and the minimum and maximum values for the angle of attack, or alpha, 1 degree and 10 degrees, and then in the middle it's 5.5 degrees, is halfway between 1 and 10. The beta, we can do the same thing for beta. That's the yaw angle. So if you're concerned about yaw stability, you might want to run a simulation at different angles of yaw to see that your plane is actually going to turn itself to face forwards instead of, something else. But I've never bothered with that, so I just set that as number of points 1 and yaw angle of 0. There's also Mach start, which is the airflow speed, so you could set that to Mach 1 if you were making a different kind of plane. I actually tried this at 0.1, which is, I think that equates to about 120 kilometers an hour, but I didn't really notice any difference, so I never bothered with it again. I just leave it at 0. So that's anyway, that's why we have 3. And for the rest of this, I'm going to start at angle of attack of -10 and go to +10, and the number of points, I'm going to set this to 21 so that we get a point on each integer number of angle of attack. Yes, 21, not 20, because you've got to consider 0, right? So let's just run that. Oh, before I do that, notice that says wake iteration 5 of 5. Let's have a look at this other viewer. So the one's called Results Manager, one's called Viewer. This is the viewer where you can view certain things such as the pressures on this wing, unsteady pressures and steady pressures. I think you need control surfaces in the simulation to have something here, but because I've never seen it more than just the one color. Vorticity, I don't really look at these much, triangulation and so on. The one thing that I did kind of like to look at in the early days when I was first getting into this program was this one. It's really boring here because we don't have many points along the wing, and also at the, well, we can change the angle of attack here to angle of attack of 10, so you can see that the wind or the air is sort of flowing at a different angle there. And at the wingtips it's a little bit You can see that the wingtip one is going up a little bit, so there's a sort of beginning of tip vortices, but there's not much resolution in this simulation. As I mentioned in the previous video, the more sections you have along your wing of these explicitly defined tessellations or divisions like that, the more time it's going to take and the more detail you'll see in this. But as I also mentioned in the previous video, don't bother increasing that too much until you get right to the end of your design cycle, I'd say. It doesn't really help much, it just slows things down. So for that reason, I'm going to just flip over to this advanced tab very briefly, and I'm going to turn the wake iterations number down to 1. And I have noticed that this doesn't make a whole lot of difference. It does make a difference, but not so much of a difference that you're going to be bothered to have it high until you get right to the end of your design process and you're starting to get fussy about things. At least that's how I do it. So now that I have 21 points, I don't want to be running 5 wake iterations every single time because it's going to be slow, especially while I'm making videos. Hopefully with just 1 wake iteration, oh, that was fast. Good. Alright, so now we have 21 different angle of attack simulations. But I don't really look at this load distribution too much. In fact, I almost never look at it, so don't worry about that. I'll just move on to this tab, which is the sweep, which is a tab that I look at all the time. And this is graphing, well, you can select a whole bunch of things along here and graph one against the other, whatever you like. And I've actually changed the source code in my program a little bit too, so that when this shows up, it showed me alpha versus moment in the y-axis by default, because this is the one that I was talking about before with my little diagrams and everything. So this is what I always want to look at, this one, and also lift to drag ratio, L over D, like that. So I've changed it so that by default it will show up like this. Normally I think the default was total drag versus coefficient of lift, so you'll see this. So don't worry if you see something different, you can just change these to whatever you want like that. I just find it a little bit easier because I'm doing it so often to have this automatically done for me, so I did it in the source code. Another thing I changed, while I'm mentioning things that I changed, is that I've made the 0 points on these axes to be a darker blue, and it's a thicker line. In the default program, all of these axis lines look the same, but I found that to be a little bit tiresome because every time I opened this graph up, what I was doing was searching along the axis to find the 0 point. It's not always in the middle. Some see it's like up there, and then on this one it's in the middle. And I was going along here to see where the 0 intersected with the graph, and then I was going down here like that. So just to help me with that, I made these a darker blue in my custom build. Anyway, yeah, so this is what this graph is showing us is along the bottom we have angle of attack, and then on the vertical graph is the CMY, which is what we could consider the pitching moment. And when this is above 0, so for example here, it means that the plane will tend to pitch upwards. When it's below 0 over here, it means the plane will tend to pitch downwards. And what we want to see is a negative slope in this graph. So as the angle of attack gets higher and higher, the plane will be more inclined to pitch downwards. And vice versa over here, as the angle of attack goes down, in other words, as the nose of the plane goes down, the natural tendency of this torque caused by the airflow around it will tend to pitch it up again. So it's going to settle on this point here. This is what we talked about just before. And in this case, for this extremely boring wing that we have, it's just basically the flat sheet example. So it's going to tend to stabilize at this point here, which is angle of attack of 0. And at that angle of attack, we can see that we have a lift to drag ratio of, well, an angle of attack of 0. The lift to drag ratio is also 0. So this is pretty useless. It's not really going to do much for us. Now, one of the reasons why it just wants to so strongly turn into the wind is because we haven't done anything with the CG yet. So this CG is set to 0, 0, 0, which is that point right there at the tip of the wing. That's actually impossible in the real world, of course. I hope you're aware. But we can set that to something else to simulate what would happen if the CG was in a little bit more sensible place. And we can do that by just typing a number into usually the xref, which is this axis here, the red one. That's usually the only one you'd need to change. Oh, by the way, I forgot to mention before, but the reason why this is CMY and not CMX or CMZ or anything is because we're measuring the torque or the twisting moment about the y-axis, which is you can see that there, it's the one that goes down the wingspan. So it's the pitch axis. That's why it's CMY. Anyway, so we can type a value in here. So let's say 1. Now there's nothing to look at, unfortunately. So we don't really get a good idea of where that is visually on here. So what I like to do is make it blank. And I'll add that here. Now a blank geom, it's not going to do anything, but it does have a location. And I'm just going to set this to 1. And now I can see that there. So like I say, it's not functional, but it just sort of helps me figure out what's going on and see if it sort of intuitively makes sense. Now that's a little bit too far forward. One thing we can do that's quite handy when we're just sort of starting out and we're not too fussy about positioning the CG exactly is we can use this calc CG button, which I think it let's see, I think it looks at the volume of this shape and averages it out and places the point there. So let's click calc CG and see what we get. 2.938, and then if I just copy that and put it into my blank, we'll see what it did. So it's, wow, that's really far back, isn't it? I'm not sure if it's yeah, I think it's just the average of the volume of the wing as a whole. Now that's too far back. Hopefully most of my viewers who are familiar with building planes will know that, oh, it doesn't look too far back, but let's see what happens when we run our simulation with the CG in the new location. Just get my windows in the right place. Alright, so let's launch Solver. Okay. Have you noticed the very important change? We still have it so that the neutral point of pitching moment is at 0 angle of attack, but something else that's very important has changed. The slope of the graph is now going upwards, and what that means is that as the angle of attack gets higher and higher, the plane is more and more likely to nose up. In other words, it's just going to flip around backwards. This is really bad. You cannot have the slope of this graph going positive. It needs to be negative. Alright, so this is not going to work. We could move it to a little bit more sensible place. What about 1.5 maybe? Let's just give myself an idea of what 1.5 looks like. That's probably a little bit too far forward, but anyway, we'll run that and see what happens. Now, hopefully, you'll also be aware that this is still not going to fly. Well, we still get intersection here is at 0 angle of attack, and the lift to drag at 0 angle of attack is 0. So what we need to do really is we need to make it so that this wing is going to angle itself upwards relative to the air. And a couple of ways we can do that. One is to use an airfoil that has a reflex in it, so that as the air leaves the trailing edge, it's going to be flicked upwards a little bit, so that the tail of the plane or the trailing edge will tend to press downwards a bit, so that as it flies along, it will be a bit more of an angle like that. So I showed you before how to change the airfoil section, so you could try that. But what I'll do for this particular example is I will add a tail, and I'll do that by copying and pasting a wing. Did that work? Yeah, so this is my tail. Stab, like that. And I will move it so that it's back here, and I will just scale it to be half the size or 40% of the size. Yeah, that'll do. Yep, that'll do. Now that's still not really going to help us, because if they're both at the same angle, it's not performing the function that we wanted to do, which was, where the hell's my other window gone? Did I close it? Alright, let's solve it. But I'll just run this anyway and see what we get. So it doesn't really change anything for us, did it? Because those two wings, or those two surfaces, are perfectly aligned with each other, so it's not going to do anything to change the way that the plane will pitch. So what we need to do to make that useful is the tail needs to be angled down a bit like that. So negative, well, I'll type it in here, -5. -5. Right, so that will hold the tail down, which would hold the front of the wing up a little bit. Something a little bit more like that. It will settle on, let's hope. So let's run that. Oh, it's a little bit slower now because we've got two wings, right? Oh, that's better. That's better. Okay, so now our point of zero moment here is at 2.6 or so degrees. And if we look at what lift to drag ratio, we're getting at 2.6 degrees angle of attack. 2.6, it's, what's that, about 14? Yeah, 14. Well, that's not bad. So this has to be positive. I forgot to mention that. Did I mention that? You need a positive lift to drag ratio if you're going to try and fly something. So between these two graphs, you can figure out whether your plane's going to fly and how efficiently it's going to fly and how stable it's going to fly. So in case it wasn't obvious, the slope of this graph, the steeper this graph is, the more strongly the plane will try and orient itself into that natural stable position. It doesn't seem to be a problem if you have a very shallow line. So let's say the line of this graph, instead of being at that angle, it started from here and it went over to here or something. That seems to be okay. As long as it's a negative slope, you should be good. So from this point on, I don't think there's a whole lot more that I need to show you, because it's just sort of a rinse and repeat cycle of twiddling and running this solver and seeing the results, and twiddling and running and seeing the results over and over and over. Oh, so that's why you want to make it run as fast as you can. Oh, that reminds me, we're going to have a look at one other setting on this tab, won't we? There's a setting here, XZ symmetry. So if your plane is perfectly symmetrical in the XZ plane, which it probably is, so just as a reminder, the XZ plane is this one here, which is straight down the center of the plane. What you can do is turn this XZ symmetry on, so that when you run it, it's only going to run the calculations for one side of the plane, and hopefully the other side of the plane will be perfectly the same. Oh, here's the load distribution, by the way. When we have the tail on, remember we angled the tail down, so it's actually going to be causing a negative load, or it's going to be pushing downwards. So that's why for the tail section, all these points in this graph are below zero on the load side. I think that's about it, really. I don't really play around with much other stuff. You can add, I'll just very, very quickly do this. I haven't found this to be useful for anything other than just visualizing sizes. So if you had a disk will be something like this, and you can change the size of it. And this is like a prop, basically. You can move the positions like that, and I only use this just to sort of visualize how big the prop is going to be and where it's going to fit without whacking into the wings or something like that. When you have a disk in your scene somewhere, provided that oh, this is the other thing that you might want to know about this tab. You can select which objects in the scene to run the VSP Aero Sim for. So if I select it, set it to shown only, and then I set my disk to be not shown, then it's going to be excluded from the simulation. But if you want it in the simulation, oh, it's gone here because I clicked no show, but hang on a minute, show game. Alright, so it popped up again here, and you can set an RPM and a diameter and a hub diameter, and I think this is coefficient of pressure and coefficient of thrust, maybe, something like that. But I've found that all it does is cause lots and lots of drag, and I tried setting the RPM to negative just in case my thrust was going in the wrong direction, but it didn't really make a whole lot of difference. So all I've really been doing is just keeping those out of it completely. Another thing that you can do is control surfaces. At risk of making this video horrendously long again, I will just briefly everything I do is briefly when it starts, but then it takes a long time, doesn't it? I haven't done much of this. I haven't found it to be too useful, but if you click on a wing, there's a sub tab under which you can choose control surf in the type and add, and now we'll see in here we have some control surfaces. I haven't found this to be useful though, so I did it once, but yeah, I just sort of think I don't really need to do it. But anyway, you can see an arrow there too, and on the other one you'll notice the arrow is going the other way. So these are ailerons linked so that when one goes up, the other one goes down. And then once you've done that, you'll see also down here a bunch of new settings that you can use to define how big it's going to be and so on. So I can change the length of it and start and end like this and so on. They're rendered a little bit strange. There seems to be some Z fighting going on there, so you can't quite see it sometimes. But anyway, so when you have those in there, under the control grouping tab of VSP Aero, then I think you do add. So now I have a group of control surfaces which can all be moved together. And I'm going to select both of these and add them. Now they're grouped, and I can give them a name, and I would say ailerons. And the important thing with the gain here is to leave that the same for ailerons. But let's say let's say they're flaps and I want them both to go the same way. Remember, we had the arrows going different ways on these two. So if you want them to go the same way, one of them's going to have to be negative. I think it'll be, I'm not sure actually. So set one of them to be a gain of negative and one of them to be a gain of positive. That will give you the behavior where they both go the same way. I know it's a little bit unintuitive because they're different here, but remember that they were different to start with. So we're reversing the difference and we're getting them going the same way. I'll just get rid of this disk and show you what you get. Delete. Just see what that happens when we run. So what I'll do is, for both of my wings, I'll increase the this. So I'm increasing the number of horizontal divisions, or oh, it only goes up to 26. Is that right? Alright, this is going to slow the simulation down quite a lot. I will also do it for our horizontal stabilizer as well. And then we'll see what happens with the wake iterations, and hopefully our flaps were going down. I'm not sure if there's any way to know ahead of time, but oh yeah, and one other thing we need to do before that is we go back to our overview tab, and now we'll see this new section, control group angles, and we have the control group that I called ailerons, which I should have called flaps, shouldn't I really, now that I'm making them both go the same way. Alright, we have flaps, and we're going to deflect our flaps at 15 degrees. I don't know if it's going to be up or down, but we'll find out now. Alright, and this is going to take a while, but I'll tell you how long this took, just to give you an idea. Oh, wait a minute. So there's a kill solver button here which you can which you can click to stop a job in progress. And the reason I'm doing that is because I only have wake iteration set to 1 still. You basically just get straight lines in those wake trailing wakes. It doesn't really do a full simulation, so I'm going to turn this up to 10. This is going to take a long time now, I think. You know what else I'm going to do? Sorry, I'm going to kill this again. I just realized we only need one angle of attack really just to get an idea of what this is going to look like. So I'm going to say angle of attack of 8 degrees, 1 point only. So I'm only going to run one angle of attack. Go. Okay, that felt like that took about 40 seconds or so. I'm not sure. Anyway, so this is our load distribution. Looks a bit funky now. And we can see that on the section of the wing that we had our flaps, the load is bumping up quite a lot. So it looks like we did get the flaps in the right direction and they're taking a lot of load. And our tail, even though our tail's just a plain old flat tail, there's something a bit funny going on at the edges of the tail. So I'm guessing that the airflow from the flaps is sort of affecting that here. See, it's in the same line of span. Anyway, what can we look at here? Oh, there's not much to look at in the sweep graph because we only did one angle of attack. So see how it's just 8 all the way along? You need to do more than one angle of attack if you're going to be looking at something on here. Anyway, what we wanted to look at was this, wasn't it? So we'll launch this and we will turn trailing wakes on, and hopefully they're a little bit more interesting than what we saw before. Still not that exciting really, is it? But okay, we can see that where the flaps are, we have deflected the air downwards. Okay, so we did get the flaps going the right way. Yeah, like I say, this is the only way that I know to actually check that I got it right, which is probably not the smartest way. And we can also see that now that we have more points along the wing, we can see some actual sort of tip vortices and some other funky stuff going on there. But to be honest, I don't really look at that this much. I don't really look at this that much anymore. It's kind of neat to look at, but whether it really helps you much throughout the design process, I don't really think it does that much. At least not for model planes. Maybe if you're making a full-scale plane that's going to be flying at Mach 1, this would be quite handy to look at perhaps. Anyway, I think I'll leave it there. This video is getting quite long, but haven't even really scratched the surface of what this program is capable of. I don't like that these videos get so long, but there's just really no way around it, I think, if you're going to try and look at how things work. Anyway, thanks for watching, and hope it was useful. Bye.